So today we're going to be talking about turbo machines. Well, what is a turbo machine? A turbo machine generally refers to a pump or a turbine. A pump adds energy to the fluid to move it or increase the pressure, while a turbine extracts energy from the fluid. Basic components that make up a turbo machine is the rotor shaft and blades. In this diagram, we can see the fluid entering the turbo machine through the shaft from the left-hand side where it meets the two rotors. A turbine consists of a moving fluid that forces rotation of the blades to produce energy, while a compressor or a pump exerts a force onto the fluid to move it. Different classifications of turbo machines include axial flow, mixed flow, and radial flow machines. An axial flow turbo machine involves a fluid moving in the axial flow direction from the inlet to the outlet. A radial flow consists of a radial flow component, and a mixed flow can be a mix of both axial and radial flows. Now for the energy and angular momentum considerations. If we consider a basic pump like a household fan pictured below, we can simplify the flow and the velocity. The blade speed U will be defined as an angular velocity times the radius. The absolute velocity V can be described as the sum of the blade velocity and the relative velocity W. The surface ABCD on the diagram denotes the surface of the blade where we assume the fluid move parallel to the motion of the blade. In diagram B, the velocity diagram, we are looking radially down the axis of rotation to observe the change in direction of the fluid. When the fluid meets the blade, it has no component of absolute velocity in the direction of the blade. But when it exits at point 2, it does. This is because the blade exerts a tangential force on the fluid in the direction of motion. Where there is some rotation in the system, torque and angular momentum must be considered as well. For steady flow, we derive an equation like the one shown, where the left side represents external torques of the control volume, and the right represents the net rate of angular momentum through the controlled surface. We can also consider shaft work in terms of the controlled volume. This is the sum of the inlet and outlet flows with respect to their directions. The sign of V theta will depend on its direction and the blade motion direction. Hence, they are the same sign and it is positive.
So now we're going to go a little bit more into pumps. The purpose of a pump is to add energy to the fluid. Pumps do work to the fluid to move it in or increase the pressure. Pumps exert a shaft torque on the fluid to move it. The motion of incoming fluid is assumed to be directed along the axis of rotation, meaning that it has no component of absolute velocity in the tangential direction. The fan blade exerts a tangential force component on the fluid in the direction of the motion of the blade, making the exit tangential component of absolute velocity non-zero. Essentially, this means that the blades do work on the fluid to change the fluid velocity to be in the same direction as the blades.
The next type of radial flow machine that we're discussing is the centrifugal pump. The centrifugal pump operates most efficiently with high heads and low flow rates, and its two main components are an impeller, which rotates, and a casing enclosing the impeller, which is stationary. You could see both of these two components in the images shown at the top of the slide. The impeller can be open or closed and includes blades arranged around the shaft. The impeller sucks in fluid through the eye of the casing, which increases the pressure and the absolute velocity. The absolute velocity entering or exiting the blade is shown by this equation, and the blade passage is equal to the vector sum of the angular and relative velocity. Here, U1 is the angular velocity, which is equal to the radius times the angular velocity, and W1 is the relative velocity. Also, the equation for the shaft torque applied to the centrifugal pump is given, as well as the power for a rotating shaft, which is given by shaft work and is equal to the shaft torque times the angular velocity. The equations for the total head and the total flow rate are both given as well on the slide.
Two other types of pumps are the axial flow and mixed flow pumps. In axial flow pumps, flow is mainly in the axial direction. It operates most efficiently at high flow rates and low heads like irrigation and drainage. In an axial flow pump, the propeller is confined within a cylindrical casing and a shaft connects the rotor to a motor. As it rotates at relatively high speeds, the fluid is sucked through the inlet and discharged through a row of fixed stator vanes. Axial flow pumps usually have specific speeds greater than 9,000. In an axial flow pump, it can cause overload of the drive motor if the flow rate is reduced significantly from the design capacity since the power input increases. Unlike centrifugal pumps where the Power input decreases if the flow rate is reduced significantly. For this and many other reasons, the axial flow pumps have lower efficiency than the centrifugal pumps. In mixed flow pumps, as you can assume, it has both radial and axial components, and it is used for applications that require specific speeds intermediate to those of centrifugal and axial flows, which is about 4,000 to 9,000.
Go.
Fans, which are closely related to pumps, are most used when fluid is air, gas, or vapor. Like pumps, there are two types of fans, a centrifugal fan, which has radial flow, and a propeller fan, which has axial flow. The flow analysis for fans is based on the incompressible flow concepts and assumptions similarly to pumps. Fans are labeled based on their location. Blowers, which are located near the system entrance, exhausters, which are located near the system exit, and boosters, which are located at any intermediate position. Performance curves for fans are given in a pressure rise graph, either total or static pressure, rather than head rise typically used for pumps. And fan laws shown below are used to compare and scale fans of similar geometries.
Now we're going to take a closer look into turbines. The purpose of a turbine is to extract energy from a flowing fluid. A flowing fluid can exert a torque on the rotor to force rotation and produce a shaft power that is available to drive generators or other devices. The blades in the turbine move in the direction of the force exerted on each blade by the flowing fluid, meaning that the flowing fluid does work on the blades to make the blades move in the same direction as the fluid. There are gas, steam, and hydraulic turbines. Hydraulic turbines can be impulse or reaction turbines, and we're going to look a little closer at both of those. An impulse turbine is used when it has high head and low flow rate. Pressure drop across the rotor is 0, so all pressure drops happen in the nozzle row. Space around the rotor is not completely filled with fluid. The torque is generated by the impulse of individual jets of fluid striking the blades. As you can see in each photo, around the rotor is not completely filled with fluid. The fluid is at the bottom, and it pushes on one blade at a time. Magnitude of the velocity of the water does not change, but the direction does. This causes a torque on the rotor, resulting in power output. Common impulse turbine is a Pelton wheel. The total head of the incoming fluid is converted into a large velocity head at the exit supply nozzle. As you can see on the slide, it gives the equations for finding the inlet velocity, exit velocity, the torque, the power, and the power output maximum of an impulse turbine.
The next turbo machine that we are discussing are compressible flow turbo machines. What sets these specific machines apart is that there is a density change that occurs from the inlet to the outlet. And there are two types of compressible flow turbo machines, compressors and flow turbines. Compressors are similar to pumps, which add energy to the fluid, and these machines cause an increase in pressure, density, and temperature. Compressors operate with continuous compression of flowing gas, and the most common types include radial and axial flow compressors. Compressible flow turbines, on the other hand, are most similar to turbines which remove energy from the fluid, causing a decrease in pressure, density, and temperature. And these may be either impulse or reaction turbines and include mixed, radial, and axial flow turbines. Considerations in energy and angular momentum apply in compressible flow turbo machines, and the turbines and compressors are shown below at the bottom of this slide.
Overall, this chapter covers the various aspects of turbo machines and their applications. The main concept associated with turbo machine deals with shaft torque and angular momentum of the fluid as it flows through the turbo machine. From this, we can create diagrams and compare the different velocities, whether that be relative velocity, blade velocity, and absolute velocity. For pumps and fans, we can use the standardized parameters and laws to compare performances. Impulse as well as radial and axial reaction turbines are explained, and aspects of turbo machines are found almost anywhere, from jet skis and computer fans to animal evolution and spaceship fuel pumps. And here is a slide with our sources that we used for websites and images.